So I just wanted to discuss only one question from that test because most of you had done it wrong. So are you able to see the screen?
Yes, sir.
Okay. So in this, what are the poles?
1 and -5.
So
No, sir.
poles are
-3 and -2, sir.
poles. S is equal to the easy one would be this one minus.
-3.
Okay, and then what are the other poles? S is equal to -2 and
-2
plus
plus
I.
or minus I.
-2 plus I, and then another pole at
-2 minus I.
minus I. Okay, then comes zeros. S is equal to
1 and S is equal to -5.
and S is equal to -5. So how do you write this transfer function? So first the numerator is the zeros.
Zeros.
So S
plus 1.
is 1, S minus 1 and S
plus 5.
plus 5, correct? Okay, S minus 1 and S plus 5 divided by, what is this? S
plus 3.
S plus 3, because it is minus 3 here, it is S plus 3. And how do you do this? So you have to multiply. So this would be what? S
plus
first one, it is S
plus 2
minus I multiplied by
S plus 2 plus I.
S plus 2 plus I. Okay, if you multiply this, you get as S square plus 4S plus 5. Okay, so this would be S square plus 4S plus 5. Many of you have done a mistake over here, taking it as minus. Okay, I think one of them made a mistake and others copied, probably. I don't know. How many of you have made the mistake or how many copied? I don't know. But this is many of the answer script shows it as S square minus 4S plus 5. See here, when you are taking this S is equal to -2 plus I and write it as S, you bring it to this side, left hand side, it is S plus 2 minus I. So this plus I becomes minus. Okay, and then this becomes S plus 2 plus I. Okay, because both are minus, when it comes to the left hand side, both will become plus. Okay, so when you multiply this S plus 2 minus I and S plus 2 plus I, you get S square plus 4S plus 5. Okay, not minus. This is wrong. Okay, so the transfer function should look like this: S minus 1 into S plus 5 divided by S plus 3 into S square plus 4S plus 5. So this is the correct answer. Okay, so many of you have gone wrong in taking the plus and minus for the I. Okay, so it is one is -2 plus I and one is -2 minus I. So when you write it like this, it will be like this: S plus 2 minus I and S plus 2 plus I, you have to multiply these two. How many of you have had got this correctly in the test? I have not gone through all the papers. Has anybody got it right? Anyone? Was the paper difficult?
No, sir. Paper was easy.
Paper was easy. Okay. See, what I had asked was, the next question was to draw the pole zero plot for the given transfer function. This was the reverse of that. Given the pole zero plot, write the transfer function. So both you must be able to do. Okay. So just this, only this imaginary part, the sign convention, this sign is wrong. You have taken. Okay, other things are fine. But have you all understood these things, or I don't know? When I see everybody writing the same mistake, I feel many of them have copied only. Okay. So see, it's not yet decided whether the final exam will be online or regular in classrooms. So please be prepared. That's what I would say. Be prepared for anything. Next will be the MCQs. When is the quiz? Quiz dates? Any idea?
We don't know, sir, to given class.
There's a calendar of events shared. Okay, please look into that. Okay. So
Okay, sir.
next would be the quizzes. So it will be of 2 modules. So most probably it will be on the root locus and the PID controllers. Okay. So start preparing for those MCQs. It will be conducted by the COE. So please be prepared for the next quiz. It's not a regular test. It's an MCQ type of 2 modules. Okay. So get prepared for that. Next is the next topic I'd like to discuss is first order systems. First order systems. So far we have discussed second order systems where zeta and omega n are the 2 important things. So in first order system, what is important we'll see. In first order system, always the step response will be exponential. Okay, the step response will always be exponential. There won't be any oscillations. Okay, so the damping ratio, if you like to say, it is equal to 1. Okay, so the step response will always be exponential. So it will be either exponential increase or exponential decrease. Okay, so this is how the first order system will behave like. What is a first order system?
Power of S is 1, sir.
Power of S is 1. Okay, there is only one pole. Okay,
Yes, sir.
one pole. Okay, so that is called as a first order system. Now as you had in a second order system, you had this g of s equal to omega n square divided by s square plus 2 zeta omega n s plus omega n square. This was the second order transfer function conventional form. Okay, so general form. Okay, so instead of a second order system, we will write it for a first order system. So that is written like, instead of the zeta and the omega n, it is written as k divided by tau into s plus 1. Okay, where k and tau are important, like zeta and omega n in a second order system, k and tau are important in a first order system. So k is called as the gain of the system, and tau is called as time constant. Tau is called as time constant. Okay, so these are the 2 things. Something like your zeta and omega n in a second order system. So first order system will have gain and time constant. So these are the 2 things which are going to affect the response of a first order system. Please make sure that you have 1 here. Okay, you should always have 1 here. Okay, k divided by tau s plus 1. It must be of this form only. Okay, you should always have 1 on the after this plus sign. Okay, so you should always have in that form to find out what is tau. Okay, tau is called as a time constant. So what is the definition of a time constant? Definition of a time constant is, it is the time taken for reaching, say this is 1, okay, the final value is 1, this is equal to 0.632, okay, the value, the time it takes to reach the 63.2% of the final output, okay, that is called as the time constant, the time taken. So x-axis is the time, okay, y-axis is the response, okay. So this is equal to tau, okay, it is equal to 63.2% of the total output is called as one time constant, okay. So this is the definition. I'm not going to do the derivation for this 63.2, but just you can remember as a definition, the time constant in a first order system is, it is equal to the 63.2% of the time taken for reaching 63.2% of the total value, okay. So that is called as the time constant. So if that is called as a time constant, then can you calculate what is the time constant for this?
Yes, sir.
So how do you calculate?
63.2% of 2, and then we draw
0.632 of 2.
2, sir.
Final value is 2. So how much is this?
1.26.
1.264.
1.26. Okay. So where do I mark it? X-axis or Y-axis?
Y-axis.
Y-axis. Okay. 1.26 somewhere over here.
Yes, sir.
Okay. So
1 second, sir.
the time that it takes to reach this, okay. So can you write the transfer function for this?
K by S plus 1, sir.
2k is equal
2 by
to 2
S
divided
plus
by
1. S
s
plus 1.
plus 1, okay. 2 divided by s plus 1, where tau is equal to 1, okay. So this is tau s plus 1, so tau is equal to 1, so it is 2 divided by s plus 1, okay. Similarly, calculate for this. Point 632 times
That is 22.12, sir. 0.63 into 35. 22.12.
22, okay, somewhere over here, okay.
Sir.
So
Maybe 3
maybe
seconds.
3 seconds something, okay. Time constant is approximately 3 seconds, approximately 3 seconds, okay, fine. In this, this is a closed loop feedback system, okay. Just take this, okay, just take only this one, 0.5 divided by 6s plus 2. What is the time constant for this? Tau is equal to how much?
3, sir.
How do you get?
Sir, we take 2
K
common.
of s is equal to k divided by tau s plus 1, okay. So if you want to have 1 here, what you should do?
Take 2
Divide by
common,
2,
sir.
okay. So it is 0.5 What is the transfer function? What is the k value?
0.5, sir.
0.5 by
0.2. Oh, yes, sir. Yes, sir.
0.25.
Divided by 3s plus 1.
3s plus 1. Okay. So tau is equal to 3 seconds. Okay. The unit of time constant is seconds. K is equal to 0.25. Okay. So what is the advantage? What do you get from this? What is the advantage of this? Can you think of any advantage of knowing these things?
Directly K value we're getting, sir.
Suppose, for example, if you are doing the system identification, okay, using a black box method. Black box method means you don't know the physics of the system. Okay.
Input output
You just
physics.
give the input and get a response. Okay. You get some response like this. Okay, for some system. Say for example, some system, you're getting such a response, step response. Okay, I'm talking about step response. So when you get such a response, how do you write transfer function? Okay, so how do you write a transfer function for such a response of a system? So when that situation arises, then you can directly use the form k divided by tau s plus 1. Okay, so looking at this, you can calculate what is the time constant, and then you know what is the value of k. Okay, so with that you can get the transfer function. So this is particularly useful when you're doing a system identification with black box method. Okay, suppose for example we did that DC motor. That was white box or black box we did?
White box, sir. We use the
Was,
physics.
yeah, so that was white box method. If you take a DC motor, apply some voltage, get some rotation, okay, get some angular velocity, note it down, and then plot it. Okay, suppose the DC motor is a first order transfer function. I'm just giving you an example. If the behavior is like a first order system, then this is applicable. Okay, so this concept is applicable only when the system is a first order system. Okay, so there is only one pole in the transfer function. Okay, so only then it will be of use. Similar to what you did for the second order system, the zeta and the omega, and that is applicable only for a second order system. Suppose you have a third order system, you approximate it to a second order system and then find out the damping ratio and the natural frequency. Okay, so similarly, this is for a first order system where k is the gain and tau is the time constant. So in this problem, what should be the value of Kp for the closed loop to have a time constant of 0.2 seconds? Okay, so this is the question. So what should be the value of Kp for the closed loop to have a time constant of 0.2 seconds? So how do you do this? Okay, so what is the transfer function, closed loop transfer function? He is asking for closed loop. Okay, so what is the closed loop transfer function for this system?
G of s into GCFS by 1 plus G of s into GCFS.
Yeah, Kp into 0.5
0.5
divided by
6s plus 2.
plus 2 divided by 1 plus Kp into 0.5 divided by 6s plus 2. Okay, so what do you get? 6s plus 2. So this would be 6s plus 2 plus 0.5 Kp. So this term and this term gets cancelled. We'll be left with 0.5 kp divided by 6s plus 2 plus 0.5 times kp. So this is the closed loop transfer function. Okay. So what is he asking? What should be the value of kp for the closed loop to have a time constant of 0.2 seconds? Okay. So how do you find time constant from this? So imagine this is like k divided by tau s plus 1. Okay. So what will be the kp value, okay, for tau is equal to 0.2?
Yes, sir.
Find out. How do you find this out? Yeah, bring this denominator in this form.
Yes, sir. Yes, sir.
You get the thing. So time constant is 0.2 is equal to what you should write here? What is the equation here for tau is equal to 0.2 is equal to?
Sir. Don't know, sir.
Oh no. Is it 6 divided by 2 plus 0.5 times kp?
How, sir?
If you put here 6 divided by 2 plus 0.5 times kp, then this will become 1, right? This term?
The denominator, sir.
Yeah, this term 2 plus 0.5 times kp.
Yes, sir.
2 plus 0.5 times kp is there here.
Okay, okay. Yes, sir. Yes, sir.
This will become 1.
Yes, sir.
6 divided by this. So that is equal to the time constant 0.2.
Yes, sir.
Okay, so now find kp. See, it must be of this form tau s plus 1. Okay, so how do you get 1 here? How do you make this term 1?
Divided by that term.
Plus 0.5 times kp. Okay, and there is 6 here, so 6 divided by 2 plus 0.5 times kp. That should be equal to the time constant. Correct?
Yes, sir.
So what is kp?
$56, sir.
So kp is 56. Okay. So this is what he has asked here. What should be the value of kp for the closed loop to have a time constant of 0.2 seconds? Okay. So what should be this value if the time constant of a closed loop transfer function? Okay. So previously what we did, this tau is equal to 3 seconds. This was for open loop. Okay. Only this one we considered. Okay. Now we consider the closed loop transfer function. So for that we calculated what is the closed loop transfer function using this formula which we always use. Okay, so we get the closed loop transfer function. From this, if you compare this equation and this equation, here if you have to get 1, then you have to divide this term. Okay, so it will be 2 plus 0.5 kp in the denominator, 6 divided by, because there is 6 here. So that should be equal to the time constant 0.2, and so if time constant is equal to 0.2, then kp will be equal to 56. That is what you have found out. Okay, so what are the things that you need to remember is time constant is the time taken to reach
63.2%.
63.2% of the total value. Okay, so that is called as a time constant, and it should be of the form k divided by tau s plus 1. Okay, always here it should be 1 only. Okay, so in this problem, when it was 2 here, we divided that here. Okay, we converted this 2 into 1 here. Okay, so it became 0.25 divided by 3s plus 1. Okay, when you have in this form only, you can take this time constant tau as 3. Okay, just don't have this transfer function like this and say time constant is 6. Okay, it is not the correct answer. Okay, so always here 1 should be there. You should bring it to that form and then find out what is tau. Okay, this is a very important point you need to remember. Then we were calculating this rise time, peak time and all those, right, in the second order system. So here also you can calculate rise time. Okay, rise time is given by 2.2 times tau. Okay, this is the formula. So rise time is equal to 2.2 times tau. Then settling time is 4 times tau. Okay, so these are the two formulas. Just note down. So for a second order system, we had some formulas for the rise time and all those. Okay, so similarly for a first order system, rise time is given by 2.2 times tau and settling time is given as 4 times tau. Okay, so and also g of s is given by k divided by tau s plus 1. Okay, and then y of t is equal to, y of t means the amplitude. Okay, 1 minus e to the power minus t divided by tau. So this is the formula for calculating the value at any given time. Okay, so if you put so you can calculate at any point of time what is the value of y here. Okay, so if you have the curve like this, okay, so this is time, okay, and this is y of t is the y-axis. Okay, so if you want to calculate the value at this point, or this point, okay, for any point of time, then you can do that with this formula. Okay, so suppose if you put t is equal to tau, what will happen?
E to the power minus 1, sir.
Yeah, can you calculate this? 1 minus e to the power minus 1.
0.632, sir.
Okay, that is what we told, that the time constant means it is 0.632 times the total value.
Rise.
Okay.
Yes, sir.
Okay, so that is from that only you get this. Okay, when time is equal to the time constant, then you get this. Okay, so when t is equal to tau, that is time constant, then the value, so it will be y of t will be equal to 0.632 times the final value. Okay, so that is what this is. Now, a temperature sensing device is stated to behave as a first order system with a rise time of 0.1 seconds. Okay, if the element is initially at a temperature of 20 degrees centigrade and suddenly subjected to a temperature of 115 degrees centigrade, what temperature will the element indicate after a time of 0.1 seconds? Okay, so what is the time constant for this? How do you find out what is the time constant?
So rise time is given. So
Okay, rise time is
divided by 2.2 will be tau, sir.
2.2 times tau. So rise time is 0.1. Okay, 2.2 times tau. So how much is this?
Point 45, sir.
0.04, I think.
Yes, sir. 0.0.
Okay,
Yes, sir.
0.045 seconds. Okay, now, so what has he given? It starts from 20 degrees centigrade, initially at 20 degrees centigrade, subjected to a temperature of 115 degrees centigrade. Okay, so this is 20 degrees centigrade. Okay, it's increasing to
115.
115. Okay, say this is 115. So what is the total increase? 95
Yes, sir.
degrees centigrade. 115 minus 20. Okay, so 95 degrees centigrade is the total value. Now, what temperature will the element indicate after a time of 0.1 seconds? Okay, so you have this formula, y of t is equal to 1 minus e to the power minus t by tau. Okay, so substitute here 1 minus e to the power minus after a time of 0.1 seconds. Okay, t is equal to 0.1 divided by tau is 0.045. How much is this?
0.89, sir. 0.892.
0.892 multiplied by this 95.
84.74, sir.
80,
84.74.
84.74 plus 20. This 20.
104.74.
104.74 degrees centigrade it will indicate. Okay, or you can do this 0.892 into 115 itself. So what you have done here is this t is 0.1 seconds that is given here. Okay, from the rise time you calculated time constant. So 1 minus e to the power minus 0.1 divided by 0.045 is 0.892. So 0.892 times of this, okay, of the total increase is 95. So it will be 84.74 degrees centigrade. Already 20 degrees centigrade is there plus 20. So the temperature that the element will indicate after a time of 0.1 second is 84.74 plus 20. It is 104.74 degrees centigrade. Okay, so have you understood this? Any doubts in this?
No doubt, sir.
Okay, I've not done the derivation part, but just I've told you what form this transfer function should be for a first order system to know the time constant. Okay, that's the first thing we discussed, and then we said what is a time constant. Okay, and then and then how to find the closed loop transfer function. You already know the formula. Okay, so these things you can do. And then we also looked at the two formulas, the rise time and the settling time. 4 times the time constant gives you settling time. 2.2 times the time constant will give you the rise time. Okay, here you don't have any oscillations. Okay, here you don't have any oscillations, so that is why there is no peak time or overshoot or anything. Okay, there is no overshoot here. Always a first order system will have this damping ratio equal to 1, and it will just after a period of time it tries to reach the final value. So this is the kind of response, a step response a first order system will have. Okay, a second order system will have all the damping, under damped systems. Okay, so those kinds it will be there, but a first order system will always have the exponential growth or exponential decay. Okay, so if you're talking about discharging of a capacitor or something, then it is exponential decay. This is exponential rise. So that is about the first order systems. Yeah. So now at 11:30, the B section will have the control lab. So in that lab, I'll be discussing about the mathematical modeling of a car. I had done this for A section last week. So in the last control lab class. So B section, I'll be doing it today. So please attend that. It will be of real application type problem we'll be discussing. Okay, so B section students log in at 11:30 for the control lab. We'll be mathematically modeling a car. Okay, any questions, any difficulties you're facing with this course?
Oh, sir.
Okay. Okay, then we'll stop here. B section students will meet at 11:30. Thank you.